Uh-oh. Where's my video? Okay, here it is. Oh, I see. Okay. Hi, everyone. How's it going? Any complaints? Let's have airing of the grievances. If you have something that you're annoyed about, you should air it now. No one? Everyone is very chill. Does anyone have their vaccine?
A friend of mine, my age, he went with his grandmother to get vaccinated. And when he was there, they were just like, hey, do you want to just get vaccinated too? And he was like, yep. And then they vaccinated him. And he's like, 24. So, and then it just.
Yeah, apparently this happens a lot.
Yeah. So if you want to get vaccinated,
it's actually part of the rules, right? Because he is taking care of his grandma. So that is technically according to the rules. But I have friends in the US who are getting vaccinated because no one wants to get vaccinated in their area. so they're taking up vaccines that no one wants. You don't know of anyone who's actually traveled to the US to get a vaccine, do you? I guess it's going to start happening soon. Okay. Daniel says that his mother's been vaccinating people. That's good.
Do people not want it because it's risky? Like you might get something worse out of the vaccine?
No, they're just brainwashed. They've been brainwashed not to get vaccinated. Convinced, in other words. What's the difference between brainwashing and convincing? Convincing, it's the same thing. I guess convincing, when you have to convince someone of something against their better judgment, that's when it's called brainwashing. Okay, so I was going to say something important at the beginning of class, but all I can remember now is the material that I'm supposed to cover. So am I right in thinking that Friday is a holiday? Some kind of a Christian holiday. Right. So then how many classes do we have left?
I guess just today and next week.
Next week being 2 classes.
Yeah.
All right, that's fine. Okay, so I'll try to explain a kind of one of the great advances, or like one of the great kind of timeless discoveries of physics. It's at the same level as, in a way, it's such an important idea and such an influential idea that it's at the same level of relativity, or of yeah, it's that fundamental. And it's Wigner's classification of particles. And the basic idea behind it is that your conception, our conception of space and time, immediately has an impact on the classification of particles. And the reason it has to do with quantum mechanics. So the logic is so Wigner classification of particles starts with the question, what is the symmetry group of physics, of the universe, of our reality? Okay. And this question about what is the symmetry group of reality, this is the thing that was changed over time. I mean, I'm not here to teach a history of physics or something, but it's quantum mechanics, so it's a historical topic already. So this idea of what the symmetry group of reality, what it is, this is the thing that has evolved through the scientific revolutions. This is the main thing that has evolved. For example, in the Newtonian world, we for Newton, the symmetry group was like SO3, rotations of three-dimensional space, and R3, translations in three-dimensional space, and R, translations in time. Actually, there's an even kind of more primitive viewpoint where you get subgroups of this, because people thought that maybe the Earth is like at a center point which must be fixed by symmetries. So they thought that maybe at the center of the Earth, there's an absolute fixed point that all symmetries must respect. So that's the, what do they call it? The egocentric or...
Geocentric model? You're talking about like...
What is it? Egocentric?
Like the geocentric model?
Geocentric.
Yeah.
Geocentric.
Basically the same thing.
And then there was heliocentric. So there's some idea that maybe certain frames of reference are privileged above others. Maybe some observers, namely the ones that are on the Earth, are the only ones that that they have a privileged status, and that physics should be written in such frames. But then with Einstein, this was enlarged to the Poincare Group. It was an observation of Einstein and Poincare. And actually, the person who really had observed it from a practical point of view, and the one who really made the the main discovery was Lorentz, but Lorentz was an old man by that time, and they weren't interested in giving him any credit. But he's the one who looked at the equations of Maxwell and realized that the symmetry group of those equations, which was basically the greatest theory of physics, the most accurate theory of physics that they had, and he realized that the symmetry group was not SO3 SNR3, but rather NR, but rather the Lorentz group, and so then the idea came from Minkowski that the way that you should interpret this is by defining is by incorporating the one dimension of time and the three dimensions of space together in one R4. And then in order to be able to tell the difference between the space and time, Minkowski suggests to put a metric, an inner product on this space, which treats time and space with a different sign. That's the way that you distinguish the difference between time and space, is that time distances have positive distance and spatial differences have negative distance. And some people use the opposite. Some people put a minus here and a plus here. But the important thing is that space and time should be treated with an opposite sign by this notion of distance. This notion of distance is called the proper time. And one way to think about this convention of keeping time positive and space negative is like this, is that if you want to travel from one time to another, you don't really have to do much. You can definitely do it. You just have to stay there and wait, and you will travel a certain amount of distance in time, and that will take a certain amount of time, and that time is the distance. So the distance that it takes, the distance you travel just by sitting in your chair is a certain amount of time distance, which is a positive quantity. Okay, but if you wanted to go instantaneously, from here to a different location, several light years away, or several 100,000 kilometers away, that would be a negative spatial distance, and that's a good reminder of the fact that you cannot do it. You cannot actually travel in true physics without having a lot of time pass, and so much time is going to pass, in fact, during your travel, that the total time as measured by this metric will be positive. So there are points in space-time that are space-like separated, which have a negative distance, but those 2 points cannot be joined by an actual observable, by an actual observer. We cannot actually have a travel between these two events. The only way we can have travel from one event to another is if they're separated by a positive distance with respect to the Minkowski metric. So the Minkowski metric is basically encoding a lot of physical information about causality and so on. And so I drew here that if you're at the origin of R4, and everyone is at their own origin of their own change of coordinates version of spacetime, there will be a spatial slice which is given by t equals 0. And then there will be a cone of directions, a cone of vectors, which have 0 norm. And the 0 norm vectors are the time-like directions. So the light beams, they travel at velocities which are 0 norm with respect to this metric. And physical observers, people with mass, they travel in directions which are in the time direction, roughly speaking. They're inside this light cone, as they call it. And no one is so let me maybe draw some of this. So a usual massive observer would have velocity in space-time pointing inside the light cone. Light or any massless particle would travel along the light cone. And then we have these fictitious, unobserved, never been observed particles, which would be called tachyons, which have velocity in the spatial direction. Those apparently do not exist. So anyway, we have this basic structure, and so the symmetry group of this structure. So this is basically just a vector space R4 equipped with a bilinear form. And if you look at the symmetries of this structure, you find that you get two types of symmetries, roughly speaking. You get orthogonal, the analog of the orthogonal group, except that because of the fact that this metric is not positive definite, this group is non-compact. It contains O1 cross O3. If you just separately look at the symmetries of time and space, it would contain that, but it has more stuff that mix time and space. And anyway, I explained this in detail in the assignment. And inside this group, we have the identity element. And if we look at all of the group elements which are connected to the identity, we get something which is called the restricted Lorentz group. So these are all linear transformations of R4. These all fix the origin, and they preserve this metric. So an observable which has a certain mass, you apply one of these transformations to it, the velocity will change, but it will remain inside the light cone. Something which has mass 0 and which moves with the speed of light, if you apply one of these transformations, it will stay on the light cone and will never come off of it. Okay, and this group has the same defect that SO3 has. In fact, it contains SO3. O eta contains O3, and this thing contains SO3. But as we know, SO3 is not the true symmetry group of physics because it has this property that it has a double cover, a universal cover, SU2, which has representations of even dimension, irreducible representations of even dimension, which apparently we need because there are particles that have spin 1/2 and that behave according to SU2 representations, not SO3. So although we're accustomed to SO3 and we're accustomed to this, and maybe I should just, yeah, okay, I'll get to that in a second. So this has the same defect as SO3, namely that it's not simply connected. It has a double cover, which is called spin 1,3. That's the spin group. And yeah, and we can even see, and this spin group, there's a coincidence of groups. This happens a lot in low dimension. And there's a coincidence in which this group is isomorphic to SL2C, which is a group that you know well. Complex 2x2 matrices with determinant 1. So it turns out that one of the most fundamental groups of all for human beings is this group, SL2C. Okay, but these are all linear transformations that fix the origin. We can also consider translations, which send a vector to a vector plus a fixed v. And if we combine these two groups, we get what's called the Poincare group. And that is the group that we today believe is the fundamental group of symmetries of nature. Actually, since Wigner, since the 30s, there's been some addenda, there's been some extra parts of the group that's been discovered. It turns out that this Poincare group has to be modified to include other groups like SU2, SU3, and perhaps more. Okay, because there are particles which have exotic properties, other invariant conserved quantities, which require the addition of extra groups. But let's ignore those because it's the same idea. Once Wigner came, then it became clear what you're supposed to do, and they just smashed their particles and got all these conserved quantities, and they figured out the groups. Okay, but but if we understand this one, then we understand the essential. Basically, we would understand the primary method by which physicists determine the elementary constituents of nature. Okay, so let's do that. Before we get into that, it's important to understand this group a little bit better. So if we look at this group, we have, so in order to see how this SL2C really acts on spacetime, what we can do is express a point in spacetime, t, x, y, z. These are 4 real numbers, and just write a linear combination of the Pauli spin matrices, which are self-adjoint operators that we studied a lot, and also the identity, which is also in there. So now we have basically 4 matrices, 2x2 matrices, and we just use coefficients, which are the point in spacetime. So we are representing spacetime points as self-adjoint 2x2 matrices. And then this SL2C matrix A will act on this spacetime point by conjugation. Really, it's AQA adjoint. Adjoint means complex conjugate transpose. And you can see that this thing is going to be self-adjoint again. This is a basis for the self-adjoint matrices. And so that's it. That's the action. And you can see that it's a group action. So we have a representation of SL2C on R4, and that is the only thing that is needed to understand the group. So I'll come back to this in a second. Yeah, the other, so there's a U1 subgroup. I'm just kind of going over what I asked you to look at. So this is going to be like the U1 subgroup of SU2. Remember, that's what we use to classify the representations of SU2. And remember that those rotations inside SU2, they corresponded in SO3 to be rotations about one of the 3 axes. So this is a usual spatial rotation, basically. And this will be another spatial rotation. Okay, just giving out hints here. This is the one that's going to be different. So this is a subgroup of, this obviously has determinant 1, if you take the determinant. T is a real number. So this real one-dimensional subgroup, there's only one parameter, T. This is a subgroup of SL2C, one-dimensional, but it's not the circle. So this is like an analog of the circle, except that it's really a copy of the real line inside this SL2C. And what this thing does, it's called a Lorentz Boost, depending on the value of T. So actually, I shouldn't have used T as a parameter. So I always use T as a parameter, but in this case, I don't want you to confuse it with time. It has nothing to do with time. So this basically is going to take space and time, okay, your coordinates, right? And it's going to so let's say that you are moving at a certain velocity, in space-time. You have a path whose derivative is this vector, right? And if you apply this transformation, then what's going to happen is that this component will be, let's say, yeah, these components will be yeah. Sorry, I was going to give a simple explanation, but let's let me just see if I can. I'll give an explicit example in a second. Basically, I'll just tell you the answer. So there's going to be, you see, if this was X and Y, rotation about the Z axis, what would it do? It would take a vector on the circle and it would rotate it by a certain angle theta. This would be rotation. This transformation, okay, it's like a rotation, right? Because it's in the Lorentz group, so it's preserving this metric, but the metric is a split signature. It's not a positive definite signature. So what it's doing is that there's the analog of the circle, right? If we have time and space, the analog of the circle would be t squared minus x squared is equal to 1, which would be a hyperbola like this. So this is the analog of the circle when you're dealing with a metric that is not of all positive signature. And so this transformation, what it's doing is it's moving your vector by a certain angle, theta, right? Or t in the description that I gave. Okay, along this hyperbola. And the physical meaning of this is that you are an observer that is changing their speed. So if you if you remain at the same point, but you change your speed, right? So that now you are an observer traveling at a particular speed, but passing through that same point, right? Then you're two different observers. Even though you're at the same point, one of you is stationary, quote unquote, the other one is moving with respect to the first. And the difference between those two coordinate charts is given by such a so-called Lorentz boost. So this changes velocity at the same point. Okay. And so what you see is that the time and, the direction of time and the direction of space, they change depending on what speed you are at relative to someone else. And so this transformation, this matrix, is the essence of special relativity. That's all contained in this particular matrix. All of the behavior of special relativity. Okay, so what? So that's all I want to say about the Poincare group. Well, okay, sorry. That's all I want to say introductory about the Poincare. But I haven't yet defined the group. So it contains R4 translations, and it contains SO3. It contains SO plus 3,1 or SL2C. Lorentz transformations. Okay. Now, one of these groups is a normal subgroup, the other one is not. The a normal subgroup is one that if you conjugate it, if you act by conjugation on it, it stays closed. It's closed under conjugation. So if you take any element of the Poincare group and you conjugate this subgroup by it, it would stay inside there. So if you if you look at how translations act on rotations. So for example, if I say, okay, if I take you, let's say that I'm at the origin, right? Self-centered. And then I take you who's somewhere else. I translate you here, I rotate, and then I translate you back. Okay, that is a transformation. It's in the Poincare group. I took an object from somewhere else, translated it here, rotated it, and then translated it back. So the result of that transformation is what? Well, it's definitely not a rotation about the origin. It's a rotation about that person's origin, not about my origin, right? So that means that the rotations are not a normal subgroup. So this is not normal. Okay. On the other hand, if I was describing to you a translation, so if I if I basically took an object, rotated it about the origin, then translated it a certain distance, and then rotated it back, maybe that's difficult to see, but the result is still a translation because all of the rotational aspect has been removed. You do the rotational part, right? And then you translate, and then you undo the rotation. So the attitude of the body would be back to the way it was. So it might be, rotating like this, and in so doing, it is rotating, right? Then I translate, and then I rotate back. So in the end, what you've done is just translate. So it's very important that R4 is a normal subgroup of the Poincare group. So in fact, the Poincare group is the product of these two subgroups, meaning that each element can be uniquely written as Lorentz followed by translation. Okay, but the translation is the one that's normal. And the interesting thing is that when you do this, right, if you so if you conjugate a translation by V by one of these rotations, let's say R is in SL2. Okay, if you conjugate a translation operation, then what you're going to get is another translation operator. By what vector? Well, it's exactly R applied to the vector. So what this means is that R, or rather SL2C, acts on the subgroup R4 of translations via the representation that I already said, that A acts on P, what did I call it? Q acts on Q via AQA adjoint. So we have a representation of a group, SL2, on a vector space, which is an abelian group, which is itself a group. Whenever we have this kind of action of a group on a group, we can form what's called the semi-direct product. Semi-direct product SL2C, the one that's acting, you have to imagine that it has arms like hands like this, and it's acting, and it's taking the things in the other group and it's switching them around. Okay. I'm trying to give you a mnemonic for how to remember the notation. The SL2C is acting on R4. Okay, we write an operator, we write an element in here. So this is the Poincare group. What I'm trying to say is that it is a semi-direct product. So what does this mean? This means that as a set, P is SL2C cross R4. And the group structure is that if we take R1, V1, and R2, V2, these compose just as they would in SL2. And these, they add like this, V1 plus the action of R1 on V2. So you see that the group structure involves the action of this group on this group. Okay, and so it's a kind of twisted version of the Cartesian product. It's the Cartesian product with a twist. Okay, this forms a group, and this is called a semi-direct product construction, and the Poincare group is a nice example of this. Actually, if you go back to Newtonian mechanics, for Newton, the group what's this one called? The Euclidean group? I forget what it's called. It's SO3, semi-direct R3. Same idea. Okay, but actually there's also time. Okay, so semi-direct products are cool, and they give rise to the Poincare group. And what's the point? So expressing P as a semi-direct product is the first step in classifying its irreducible representations. Right? We need to classify the irreducible representations. This is Wigner's main idea. Let me just go over the logic, recall the logic. I mean, I mentioned this a bit. So Wigner's logic is like this, that P is the symmetry group of physics. Quantum mechanics has state space, a vector space, let's say big V. Therefore, P must act on V, and the elementary particles are quantum systems which are P irreducible. That is the philosophy of Wigner, and it's the philosophy of modern physics. Elementary means irreducible. Okay. Okay, now you need to, it turns out that mathematically speaking, there's a lot of representations. There's representations that that are so behaved, that they behave in a certain way that they do not preserve the inner product. So, so there are some additional hypotheses which you need to plug into this logic. In particular, the most important one is that they should be unitary, and they should depend continuously on the group element. We don't want a crazy representation so that that if you change the group element smoothly, right? If you think of it as a 2x2 matrix, the entries of the matrix, if you just change them smoothly, smooth functions of some other parameter, then we would want the representation matrix to also change smoothly. Okay, if you do away with that assumption, there's yet more crazy mathematically constructible, representations which do not occur in physics. So anyway, with a few minor modifications, Wigner's logic is the primary focus. That's how we figure these things out. So what we need is a method for constructing irreducible representations of semi-direct products. Okay, and this surprisingly was pretty much first done by Wigner, and then it was generalized by Mackey, vastly generalized in representation theory for all kinds of different groups and so on. But the basic idea is basically, we could call it, there's a method which is, it goes by a few different names. One way is called the orbit method. Another way of calling it is induced representations. Okay, but anyway, it's not so important. Okay, so let me just, so it has to do with, okay, not surprisingly, the way that you find representations of this semi-direct product is going to be very closely related to finding representations of this group and of this group separately. That's the basic idea. Okay, now this group is abelian, and we already saw that representations of an abelian group are one-dimensional. So that means that a representation of this translation group is going to be very simple. And then representations of SL2C, well, we already studied the representations of SU2, and the representations of SU2 are basically the representations of SL2C. So there's no, the representations that we're interested in are actually the representations of SU2, which are sitting inside here, inside this SL2C. And so what we're going to do is combine representations of SU2 with representations of R4, and we're going to include something about this semi-direct product. Those are the three ingredients. So the ingredients are, number one, the action of SL2 on R4. So this is, yeah, in the semi-direct product. Number two, the representations of R4, which are one-dimensional, since it's an abelian group. Remember, we had Schur's lemma. And then the representations of SU2, which are sitting inside SL2C. And these are going to be the good ones because we want unitary representations. So that's going to allow us to break our group down to SU2. these are the three ingredients. And we basically have, everything needed in order to proceed. So let me explain the method. I only have 10 minutes, unfortunately, to explain the method. But okay, so step one, we need to find the orbits of the action of SL2 on R4. So if we take a point in R4 and act by the group, where does it go? Where does it get sent? Well, notice that, so the representation, this is a representation SL2C going to linear maps on R4, transformations of R4. And remember that it takes A to A. So if I write P as this T E plus X sigma 1 plus Y sigma 2 plus Z sigma 3, it goes it goes to the transformation P goes to A P A adjoint. And notice that this determinant of P is fixed by the action. But what is the determinant of P? It's exactly T0 squared minus T1 squared minus T2 squared minus minus X squared minus Y squared minus Z squared. And let's call this, so actually I'm going to change the notation a little bit, because I'm going to think of this R4 as the velocity vector, or sometimes called the momentum vector of the particle. So I'll call this P0. This is the direction of the particle's motion in the time direction. This is the momentum in the X, Y, and Z directions. And that's why here I had, it's better to use P0 squared minus P1 squared, P2 squared minus P3 squared. And this, I'm going to give it a name, which is M squared, which is the typical physicist's way of writing it, even though it doesn't necessarily have to be positive. But it is in physics. Okay, so the mass, this is what they call mass. The mass is the value of this invariant quadratic form under the action of the Lorentz group. So this means that, as a kind of sketch of the situation, I'm going to have these regions. So these are different values. Here I'm trying to draw maybe one dimension of time and two dimensions of space, but yeah, so you see that the different values of this parameter, this one is m squared positive. This one is m squared equals to 0, and this would be m squared negative. Okay. And this would also be m squared negative. Okay, so we have this thing here. This is an orbit of SL2C in R4. And let's see, the other orbits, this one, oops, this is invisible. This is another orbit, except without 0. This 0 point is another orbit. And this is another orbit. Okay, I'm just trying to demonstrate that the orbits are the connected regions which are sent to themselves by the action of the group. So, and this one here, this is the one that physicists like, the green one. This one here, which is positive mass, this is called the mass shell. So people in physics, they like to talk about whether something is on or off the mass shell. And that's what they mean. They mean that the momentum, the velocity of the particle is on this one of these green shells. I mean, there's many of them, depending on what the value of the mass is. And if it's a light particle, I mean, if it's a massless particle, then it will be on the light cone. So this one here, the light cone. Okay. Okay, and then what do we do? So then what we say is, well, okay, so this thing, so we have this group SL2C, number 2. Let me explain number 2. SL2C acts on an orbit, and if we choose a point, P, on the orbit, it has a stabilizer subgroup, which is called the Isotropy Group at P. And in physics, it's called the little group. Okay, and so if I pick a point somewhere here on the mass shell, I can ask, what is the subgroup of elements in the Lorentz group which fix this point and do not move it around? And you can tell that there's got to be some subgroup there because this mass shell has only dimension 3, whereas SL2C has dimension, it's 2 by 2 complex matrices. So 2 by 2 complex matrices is already 4 complex numbers. That means that it's 8-dimensional, but the determinant is 1. So that's 1 complex condition. So that's 6. So it's 6 real dimensional acting on a 3-dimensional space. So if I look at the fixed point, the stabilizer subgroup has to be 6 minus 3-dimensional. And that's going to be 3-dimensional. So there's got to be a 3-dimensional subgroup. And that's, so for particle on the positive mass shell, okay, this group, the little group, is SU2. So there's an SU2 inside SL2C, which fixes a point on the mass shell. Okay. And number 3 is that we choose a representation of the little group. Well, we know what those are. We spent so long classifying them. So VL, spin L representation. And okay, and now, I mean, I'm already over time. I'm sorry, but that's all the ingredients. So the way you should think of it is like this, that we have the mass shell. We have a point on it. And we have a representation of the little group. And I'll draw that as a plane or a vector space sticking out of P. Here's a vector space representation of the little group. Okay, so this is the idea. So the idea is that we would like to take this vector space, and you have to loosen up a little bit to understand the explanation I'm going to give. It's going to be a little bit hand wavy, but it's the correct explanation. So we want to take this vector space and we want to spread it around all the points on the orbit. Okay. And in order to do this, I need to be able to translate a vector here. If I move from P to P prime, I need to be able to take that vector and produce another vector this way. So what does this mean? This means that I want this vector space to be a representation of the translational group, which remember is an abelian group. Okay, if we arrange that this vector space has a representation of the translational group, which is the other part of the semi-direct product, that means that we will be able to assign to each point a vector space. And between these vector spaces, we're going to be able to transport vectors. Okay, and so this result, the resulting space is what people call a vector bundle. It's going to be a bundle of vector spaces, one over every point. Okay, and so it's going to be a family of vector spaces, one associated to each point. And then what you're supposed to do is define a vector space, which is all functions. And you can, and here you can talk about continuous, C infinity, or L2 as your choice, depending on what you are trying to do, all functions from the orbit to the vector spaces. So this means that we should choose for each point on the mass shell, we choose a vector. For this point, we choose another vector. For this point, we choose another vector. And this forms a vector valued function. Okay. Okay, and what you can see is that because of the way that we built it, okay, it means that you will have an action. This has a canonical representation of the semi-direct product SL2C R4, because basically if I need to depending on what the SL2C, so for example, if the SL2C element, if I'm at a certain point on the mass shell, and if the SL2C element is trivial, that means that I'm not really moving, and I can just translate on that vector space. Okay, but if there is a non-trivial rotation, then that means that my point will be moved to a different point on the mass shell by this SL2C. Okay, but that's okay because I know how to transport my vector over here, and I'll be able to figure out how, what this group element does. And so in the end, the irreducible representations, I'm not going to give a proof of this, but the irreducible representations are classified by m squared, a certain number, and L, a certain spin. And then there's other cases where the mass squared is equal to 0, and you can even classify the ones where it's negative. But basically the point is that the representation theory of the Poincare group the Poincare group is a semi-direct product. The action of SL2 on R4 has orbits, which are these hyperbola. And the positive mass hyperboloid, that's the one that we are all on. Depending on our mass, we're going to be on a different shell, a different mass shell. And as we rotate the lab and speed up the lab and slow down the lab, we're moving around on that mass shell, okay? And all of the quantum system, the wave function of me, let's say, will be one of these functions. It will be a function on the mass shell for my mass, right? And as I rotate my lab, I'm going to be changing the wave function according to that motion. And it immediately tells me that if you're going to be elementary, that elementary particle has to have a mass and it has to have a spin. And so it gives you all the possibilities. It could be spin 1/2, spin 0, spin 1, and so on. So this is how you classify particles. So we know that we know that particles are classified by other quantities too, like the electric charge, the baryon number, the what is it called? The charm, or I forget what the modern usage is. The thing about the quarks, which quark it is. And these are other parameters which occur when you enlarge this group by adding SU2. You have to add to this U1, SU2, and SU3. This is totally separate from this SL2C. We have another SU2, which is the weak force SU2. And there's an SU3 and a U1. And if you then classify the irreducible representations of that thing, there's going to be other orbits. And these orbits will be measured by certain parameters, and that will tell you those other parameters. And that's the way that classification of elementary particles goes. Okay, sorry that was a little bit vague, but I think it's more important for you to see the idea. And the place that I recommend to see a description in detail is this book by Sternberg, Group Theory and Physics. Okay, I'll leave it there and let's go to office hours. Any questions? Oops, there's a lot in the chat. Let me write it. For more details,